Welcome to the Walton Pi. Today we are going to be talking about the Schröder-Bernstein Theorem. We're going to talk about what it is, go through the proof, and then go through an example of how we can use it. So to start off, let's define what it means for the cardinality of a set A to be less than or equal to the cardinality of a set B. So we say if there is an injective function from A to B, then the cardinality of A is less than or equal to B. And if no bijection exists, but there is still an injection, then we can say that the cardinality of A is strictly less than the cardinality of B. So, for an example, if A is the set containing 1, 2, and 3, and B is the set containing A, B, C, and D, the function which maps 1 to B, 2 to D, and 3 to A, since that is an injective function, that tells us that the cardinality of A is less than or equal to the cardinality of B. Now, you may think that this is a very simple example, and it is, because this is a finite, both sets are finite, which means we can simply count the number of elements in each set and get the cardinalities. But if we're dealing with an infinite set, or two infinite sets, then we can't always be able to just count the elements. Sometimes we might have two uncountable sets, and we have to tell which one is bigger. And that is where this injective function is going to come into play. So for example, let's say that A is the integers and B is the real numbers. And our injective function is f of x is equal to x. Because it's injective, that tells us that the cardinality of the integers is less than or equal to the cardinality of the real numbers. However, since we've proven in a different video that there is no bijection from the integers to the real numbers, we know that the cardinality of the integers is strictly less than the cardinality of the real numbers. Now that we've established what it means for cardinalities to be smaller than others, let's go through what the Schröder-Bernstein theorem says. It says that if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then the cardinality of A is equal to the cardinality of B. If we're thinking of this in just finite cases, then this is going to be pretty straightforward. If a number is less than or equal to another number, and if A and B are both numbers, if A is less than or equal to B, and B is less than or equal to A, then that means that A must equal B. However, when we're dealing with infinite numbers, this is not always super straightforward. There are different sizes of infinite sets, and just saying that both of them are infinite doesn't really tell us anything about that. And so that's where this Schröder-Bernstein theorem comes into play. We can also phrase the Schröder-Bernstein theorem in terms of just injections and bijections. So the Schröder-Bernstein theorem says if there is an injection from A to B and a different injection from B to A, then there exists a bijection from A to B. It doesn't tell us how to find it or what it is, it just tells us that a bijection exists. And so if that's all that we need to know, we don't actually have to go about and find the bijection. Sometimes it will suffice to prove that the bijection exists. So one way to visualize it is to think about A and B as different sets, and then we are sending different elements in one set to different elements in a separate set. So in this diagram, we have a set on the left and a set on the right, and the red arrows are representing the injection from our left set. Maybe that set is A. So the red is representing the injection from A to B, and the blue is representing the injection from B to A. We can then use this to kind of visualize how we might go about trying to prove this, how we might go about proving the Schröder-Bernstein theorem. So if we only have the two injections, F from A to B and G from B to A, how might we be able to go about constructing a bijection H? Well, let's look at the different cases that we might deal with if we start with an element in A. So let's say we start with this element A0 in our set A, which is on the left, and B is going to be our set on the right. So, starting with A0, we know that our function f sends A0 to something. So we now have some element in B. Our function g tells us, well, that's going to come back to A, and then we're going to repeat this process until we figure out what situation we're dealing with. So it might go back and forth A, and then back to B, and then back to A. And if it does that, in this case, we have a loop, which is one possible situation. So we might have a loop. So it starts at A naught, goes back and forth through a few elements, and then eventually ends up back at A naught. We might also end up with a chain that starts in A. So it might start with A naught and then just continue on forever and ever, never repeating elements, but it started with something in A. It might not have been A naught, but it started with some initial value in A. We might also have the same situation where it's in B, but instead of starting in A, there was some original element in B. So we have a chain that starts in B. That's another possible option that we could have. The fourth option is we might have an infinite chain, where it goes infinitely far in both directions and never repeats. Now, we have these four cases, and you might wonder, are there any others? It turns out that there aren't going to be. You can go through and try and rationalize why that's going to be the case. I'm not going to go into a great deal of detail with it in this video, but these are the only four cases we end up with. If we had any other situations, one of our premises would have broken. Either our function f wasn't injective, or our function g wasn't injective, or they weren't functions. One of those would break if we came across any other situation. So now that we've broken our problem up into four cases, let's go through how we can construct a bijection on each of these pieces, and then we can use these four bijections of subsets of A and B to construct a bijection from all of A to all of B. So we are going to write the set of elements in A which form loops as A subloop, and the elements in B that are in those loops as B subloop. And so each of these loops, we are going to have a sequence of elements that starts at some point A naught, goes to B naught, then A1, B1, A2, B2, and so on, until it cycles back to A naught. So in these loops, we need to define a bijection. So we are going to define H from A to B as H, so H subloop, so our bijection on our loop, as H of A sub k is equal to B sub k. So it's just sending A sub k to the very next thing in the loop. So A sub 0 goes to B sub 0, A sub 1 goes to B sub 1, and so on. What we now have to do is we have to prove that this function is a bijection from A loop to B loop. Let's go through this together. The first thing we need to prove is we need to prove that H loop is injective. So assume that H loop of A is equal to H loop of A prime. Defined H of A and H loop of A to be just the next element in our loop. But our loop was defined in terms of f and g. So it sends things in A to things in B through the function f, which means that H loop of A is really just a fancy way of saying f of A. And that means we now can write H loop of A equals H loop of A prime as f of A equals f of A prime. But since f was injective, that tells us that A equals A prime, which tells us that H loop is injective. The other thing we have to prove to show that H loop is a bijection is we have to prove it's surjective. So start with any element B in B loop. That means there's some loop where B goes to some value A, so like B to A1, to B1, to A2, and so on, until eventually it gets to an A prime, which then maps to B. So that means that here, our loop, the element that comes right before B, is some element in A. So we are going to define H loop of A prime to be B. So we have found an element in A that maps to B, so that tells us that H loop is going to be surjective. Specifically surjective and injective on the elements in A loop, where A loop and B loop are the elements that show up in one of these loops. And so that's the proof for H loop being a bijection. We now have to define three other bijections on each of those other situations. One of those is the A chain. So we are going to write A sub A and B sub A as the set of elements in A and B respectively, where they are elements of a chain that starts in A. So as long as they show up in a chain where the very first element in that chain is in A, it's going to be in A sub A or B sub A, depending on if it's in the set A or the set B. So here we are going to define our function h sub A as h sub A of A is equal to B, where the very next term in that chain. We now have to prove it's a bijection. Very similar to the last proof, this is going to follow a very similar structure, except it's going to be a little bit different because we are dealing with slightly different situations. Take a moment to try and prove that h sub A is a bijection from A sub A to B sub A. Okay. To start off, we're going to prove it's injective. Well, just like in our first case with the loop, h sub A of A and h sub A of A prime, those are just fancy ways of writing f of A and f of A prime. So since f was injective, A equals A prime, which tells us that h sub A is going to be injective. We are then going to show it's surjective. So we start by picking any B in B sub A. That means there's some chain that starts with A naught, goes to B naught, to A1, and so on, until eventually we get to A prime, which goes to B, which goes to A double prime, and so on. So we just look at the element that came right before B. Well, that element is A prime, and so we have found an element in A, specifically an element in A sub A, where h sub A of A prime is equal to B, which tells us that h sub A was a surjective, which tells us that h sub A was a bijection from A sub A to B sub A. Now, we're going to do the same thing with the B chain. However, this function is defined a little bit differently, because instead of starting at A, it starts at something in B. So, here we are going to define our function h sub B of A sub k as B sub k minus 1. So it's, instead of going to the next term in the chain, it goes to the previous term in the chain. We now have to prove that this is going to be a bijection. So this time, this is going to be a little bit different than the last case. So give it a shot and see if you can figure out how you might be able to prove that this is also going to be a bijection. Okay, to start off, let's prove that h sub B is injective. So, start by assuming that h sub B of A is equal to h sub B of A prime. Since G is an injective function, there is only one element B in the set B that maps to A. So, h sub B of A is going to be this element because B came right before A in our chain. B came right before A in our chain. So h sub B of A has to be this element, as it's the only option that can then map something to A via the function G. But h sub B of A prime is also going to have to be that same element B, because the two were equal. Now, since G was a function and B can only map to one element in a function, that tells us that A must be equal to A prime. So that tells us that h sub B is injective. We now have to show that h sub B is surjective. So start with any element B in B sub B. That tells us there's some chain where B shows up somewhere in that chain, where it is B sub minus 1 goes to A sub 0 to B sub 0 and so on, until we get to an A prime to B to A double prime and so on. Well, the element that comes right after B is G of B, which in this case we are writing as A double prime. So h sub B of A double prime, or h sub B of G of B, is equal to B, which tells us that h sub B is surjective because there is an element in A that maps to B, which tells us that h sub B is a bijection from A sub B to B sub B. The last case we have to deal with is the infinite chain. So we have a whole bunch of elements before we get to A0, then B0, then A1, and so on off towards infinity in both directions. So in these chains, we are going to just define h sub infinity of A sub k to be equal to B sub k. We now have to prove that h sub infinity is a bijection from A sub infinity to B sub infinity. So give it a shot, and then we will go through it together. Okay, let's go through this one together. So we start by assuming that h sub infinity of a is equal to h sub infinity of a prime. That tells us that f of a is equal to f of a prime, and since f is an injective function, that tells us that a must be equal to a prime, which tells us that h sub infinity is injective. To prove it's surjective, start with any b in b sub infinity. That means there's some infinite chain where b shows up. So, because it's an infinite chain, there must be something before it, which is, in this case, we're writing it as a prime. So that tells us that h sub infinity of a prime is equal to b, which tells us that h sub infinity is surjective, which tells us that h sub a is a bijection from a sub infinity to b sub infinity. Now that we've shown that each of those h functions were bijections, what we now need to do is we now need to construct our overall bijection h out of our h loop, our ha, and so on. We're going to define h piecewise so that h of x is equal to h sub a of x if x is in a sub a, h sub x is equal to h sub b of x if x is in a sub b, and so on. Once we have done that, what we have left to do is we have to show that no element is in more than one of our subsets, and that every element is in at least one of the 4 subsets. The reason we have to do these two pieces, we have to show it's not in more than one, because if it was in more than one, then maybe we would have a problem where this might not be a function. Because for example, if something is in both a sub a and a sub b, then it might be that under h sub a, the element goes to one thing, but under h sub b it goes to a different one. So we have to show that it's only in one of the subsets in order to show that it is actually a function. And then to show that every element is in at least one of the subsets, that is to show that it's actually a function from our entire domain A to our entire domain B. So let's start by showing that no element is in more than one of the subsets. Well, if it was in more than one subset, then two chains or a chain and a loop would have to intersect. But since the chains were constructed using injections, the only way for chains to intersect would be for the previous element to also be the same, which eventually would then imply that the entire chains were the same, which would be impossible, because we can't have a chain that starts in A and B at the same time, for example. Nor can we have a chain that starts in A also be an infinite chain, because that would also be impossible. So in each of these cases, we get these contradictions, which tells us that no element x in A is in more than one of the subsets of A. We still have to show, though, that every element is in at least one of the subsets. So, since f is a function from all of A, that means that f of x must equal some b in our set B, which means that x is a part of one of the types of chains. Either it started in A, or there was something that went to A, in which case it's either infinite, a chain that starts in B, or a loop. And so in any of these cases, x has to fall into one of those subsets of A that we care about. Putting all of those pieces together, that tells us that our piecewise function h is a bijection from A to B. Now, what were we trying to prove with all of that? We were trying to prove the Schröder-Bernstein theorem, and we have. We've successfully proven that there exists a bijection from A to B, which tells us that if we have an injection from A to B and another injection from B to A, we know there exists a bijection from A to B, even if we're not able to find the specific formula for that bijection. So let's go through and use the Schröder-Bernstein theorem to prove that these two intervals in the real numbers have the same cardinality. So let's prove that the double closed interval from 0 to 13 and the open interval from 3 to 2 unioned with the half closed interval 7 to 14 have the same cardinality. Well, one way is to try and find a bijection, which, trust me on this one, is going to be a bit complicated. If you don't believe me, give it a shot. It is possible, but it is going to be pretty tricky to do. An easier way is to use the Schröder-Bernstein theorem to construct an injection from 0 to 13 to the union of those two intervals, and then to construct a separate injection from those two intervals into 0 to 13. So let's construct an injection from 0 to 13 into the interval from -3 to 2 unioned with the interval from 7 to 14. If we define our function f by just dividing every value by 20, we are able to show that this is going to be an injection. And that tells us that the cardinality of the interval from 0 to 13 is less than or equal to the cardinality of our other set. Now, if we can construct a second injection from our two intervals into the interval from 0 to 13, that's also going to show that's going to show the second piece of the Schröder-Bernstein. If we define that function to be 3 plus x over 2, that is also going to be an injection. Now that we have these two injections, that tells us that there must be a bijection between the two, and that tells us that the two sets must have the same cardinality. I hope this video was helpful to you to be able to understand the Schröder-Bernstein theorem. Please check out some of my other videos, and please like and subscribe if you have not already, as it helps me out quite a bit. Good luck with all of your math, and have a great rest of your day.